Hello, everybody. This is a video on the creation of magnetic fields. So I'm going to keep this short and sweet. The model of magnetism created by names like Michael Faraday, James Clerk Maxwell, who I will share a little bit about in class, but really we're focusing on what this model is, what it does, kind of looking at it through fresh eyes, and just playing with it. Because there's so much to do there. So that's where we're going to spend most of our time. The whole concept of the field theory is that a current, call it I1, through a wire. Remember, a current is the flow of charge. So moving charge. Notice those two words, moving as in velocity or current. Both of those are a vector. Charge as in Q. Moving charge creates a magnetic field. One creates magnetic field, and we'll say two feels a magnetic force. That's an FB, magnetic force, due to another field. By the way, B is magnetism. B field, I1, therefore creates B1, and B1 creates a magnetic force, FB, on another current I2. That's the field theory. So the magnetic field for any current is the magnetic permeability times the current over R. In class, we talked about why it's over R. In this video, I'm just going to say it's because it's distributed over a cylinder. So if I have a current here, the cylinder is the magnetic field. As we're going to see, the magnetic field points in these directions. And it gets weaker as you get farther out because it gets distributed over a bigger cylinder. So the current is what's creating the field. These arrows are the field, and they get weaker as R because the area here of this cylinder is 2 pi R times the height, so it goes down as R, not over R squared. Now the unit of magnetic field is a Tesla. That corresponds to the unit of current, which is an amp. And of course, the unit of R is still, as it always was, the meter. Good old meter, second, kilogram, joule, Newton. You guys know all these. Now we have a new one, Tesla. Kind of a cool name, isn't it? Obviously, Nikola Tesla, you might have heard of, is famous for his studies of magnetism, electromagnetism in particular. And yeah, the name stuck, right? The magnetic permeability is defined. This is an exact definition. It's one of the few constants that's actually defined. This actually defines a Tesla. A Tesla is 2 times 10 to the negative 7. Sorry, it's 2 times 10 to the negative 7 Tesla occur a meter away from 1 amp. So here's, let me say that again. So if I have a current here of 1 amp, and I go a distance 1 meter away, then I get a magnetic field that points around in a circle like this, which I'll talk about. Right here, it's going to point into the page. The magnetic field points into the page, and magnetic field will be 2 times 10 to the negative 7 Tesla exactly. This defines what a Tesla is. It's one of the few constants that's defined as opposed to measured. Anyway, so you might say, how did I draw this? So that's the equation, that's the kind of the theory. So what's the drawing? So the right-hand rule, number one, is the right-hand rule to determine how to create a B field. And there's two steps. You take out your right hand, you make sure your right hand is perpendicular. Sorry, your right thumb is perpendicular to, here's your palm, right? Here's your fingers, your fingernails on the other side, right? Here's your thumb. You can hold it in front of your hand, like in front of your face like this, look at it. You can obviously turn it, your elbow will turn it, but your right hand needs to be open, right? Perpendicular, thumb not closed, open, and not fingers open like this. So thumb open is what I mean. So your thumb points in the direction of the current, which has a vector direction because it's a flow. It's a movement of charge. Once again, moving charge, right? This is easy. Keep it easy. Just everything on here is extraordinarily important. If you just be exact in understanding these steps, you'll be just fine. But magnetism requires that. Without that, you might get a little lost. It's easy though, if you just follow the steps. Thumb in the direction of current, and then your fingers curl. Know that I'm creating the magnetic field here. This is not the magnetic force. That's step two. So be careful. Your fingers then curl in a circle, circular around the wire in the direction of the magnetic field. All right, so pause that if you need to. So for instance, if I do have a wire going up, I have a dot to mean out of, like an arrow coming at your face. You see the tip out of or toward my face, and X is into the page or away from my face. That's like the feathers of the arrow going away from me. So here, if I have a current going up I1 and I want to draw the magnetic field in red, I'm going to have my thumb go up and my fingers curl around the wire like this. So in front of me, it points to the right. Now this is in 3 dimensions. Here, it's going to point into, away from me. Behind, it's going to point left. And here it's going to point out of. So it creates a circle around the wire. So specifically, it's X's here and dots here. And the X's get weaker with distance. You can draw that as smaller X's, I guess, or you can draw it as farther away X's. Here you can draw it as like farther away dots, and here it's really dense, big dots, I guess. It depends on how you like to draw your dots, but here it's dots. And so there'll be a circle here where it goes in, left, out, and right. Technically in is an X and out is a dot. Be careful, please, you must use these because we need to have exact positions of vectors to determine the resulting force. This is field. This is not force, but we need field to get force on another current. That's it. So if I look at this from another angle, for instance, if I have the current going away from me, have your thumb go away from you, straight away from you, your fingers curl clockwise around, and hopefully it's pretty straightforward to see that at this exact point, the field points to the right. At this exact point, it points downward at an angle to the right. At this exact point, it points specifically downward, and so forth in a circular fashion. Now, the circle is not moving. The current is moving. The magnetic field is stationary. But it orients in a geometry that looks like a circle. So if I say, what's the magnetic field at point A? The answer is left. B at A is mu I1 over R, whatever R is, to the left. And you can plug in the numbers and you know it's to the left because my fingers curl to the left underneath the wire. So you literally turn your fingers like a crank until you get to the point, like this point it's down, and this point it's left, and this point it's up, and this point it's right. Try it right now. Pause it until you get that, until you can reproduce this. And if I go twice as far away, it's half the value. So here at point B, or call it point D, B at point D will be half if this is 2R away, half of B of point A, and to the right, of course. That's it. Okay. So now that we're there, let's create a magnetic force. And I just realized that's it, right? So how do we create a magnetic force? So magnetic force is, well, you need to know the magnetic field creating the force. An object will never feel its own field. The field creates a force on another current, right? Remember? I1 creates B1. Will I1 feel its own field? No. Now, a different part of the wire, you can consider a different wire if we do like a loop, and like how does the field affect itself is an interesting question. Or how does the field from one part of the wire affect the field in another part of the wire? Can you treat it as a separate wire? In some instances, yes, and you do. You just treat it as separate parts of a wire, but don't overthink that. An object will never feel its own field is better to remember. And that creates a force on another current. So let's do that. Needs to know B and need to know I2. Or Q2 and V2. In other words, if we need a moving charge, you can either have a current, which is a flow, a steady flow, or a singular charge will still feel a magnetic force. It doesn't matter. You can have a single electron moving in this direction at some velocity v, and it's like its own little mini current, isn't it? Right? A singular proton moving is like a little bit of current. It's the tiniest almost unit of current you can get. And you can say, okay, that charge per time, right, is a little value for I. And so we can actually do this for a singular charge or a steady flow. That's supposed to be a vector sign. So how do we do this? So first formulas. The current times the length times the magnetic field is the value. If I substitute in Q per time times length times B, length per time is velocity, right? So I can do also the charge times the velocity times the magnetic field. L is the length of wire, length feeling B. In other words, if I have a magnetic field from some other thing, some B1, and I2 is here, and B1 is only in this section, then I would take this length. And you'll see this is in some standardized tests. I'm not really going to mess with this too much, but standardized tests tend to want to test your ability to calculate via formulas. So they want to test your ability to understand what variables are, which is a useful skill to have. Tests are, not evil. They're intelligently based. But the point is, I don't think we're really not going to overthink this. But it does matter that if I have the magnetic field only acting on half the wire, then that should make sense that it's only going to feel half the force. Because if I only have it acting on this section, then only these charges are feeling the magnetic field. Whereas if I double the length, then it's doubling the force. And careful, that doesn't double the current. The current is the flow, right? And the field is the external field creating the force. So this is force, this is current, this is length, and of course this is in meters. And this is the field in Tesla. So newtons, amps. A newton is an amp times a meter times a Tesla. What? So we have newtons equals amp times meter times Tesla. have fun with the units in your own time. I invite you to. So a Newton is also a Coulomb times a meter per second times a Tesla, because a Coulomb per second is an amp, as you may recall. So that's it. That's the formulas. These are Newtons. Great. Now the concept. This is the most important part. Okay, to feel FB, we'll start here. The magnetic field must be perpendicular to the current or to the velocity. If V or I, so again, same thing, if you have an individual charge or a steady flow, is parallel to B, then FB is 0. This is an observed fact of the model, or should I say it's a result of the model that is observed, however you want to look at it. Remember, the model was created to observe that parallel wires attract. You might say, wait, aren't those parallel? But careful, those are parallel wires. That's not parallel to the field. This is parallel. Because remember, the field circles around it. And so you have the wire, that's what I'm saying, step by step. Careful, guys. You need to know the magnetic field. Current 1 creates a field like this, right? Current 2 feels the force. So careful. Parallel wires does not mean parallel to the field. See what I mean? We're going to do an example in class, but I'm just going to start us off with this theory first. So the right-hand rule number 2 is how to create I was going to say create an FB, create a magnetic force, because that's how you read this, create a magnetic force. So this, you must have a flat hand, no curling here. I always say between the right-hand rules, they are not the same. There was right-hand rule number 1, that's completely different than right-hand rule number 2. Thus, number 1 and number 2, they're completely different things. This is for creating magnetic field. This is for creating magnetic force. They are different. Here, you must have a flat hand. That must look like this. Again, thumb open, right? Palm here, right? Perpendicular. You must have it be perpendicular, okay? So you have 3 vector directions. I'll draw it in the diagram first. Your thumb is still in the direction of current, but this is now I2. This is the one feeling. Remember, we need to know V2 or I2. Right? You need to know, sorry, where am I? You need to know I2 or V2, right? You need to know B1, creating the force, and you need to know the one feeling it. Careful. One is creating, one is feeling, right? So this is I2 or V2 vector. The fingers are the field, B1. And your palm, which is in third dimensions, is in the third dimension, is the force. So here's how you do it, right? So step 1, thumb, flat hand, thumb in the direction of I2 or V2, depending on if you're dealing with a velocity or a current, same, it's just flow of charge. And this is for positive charge, guys. That's the convention we're still dealing with. 2, fingers field. I'm sticking with red for the numbers here for some reason. All right, fingers are still field, but it's flat hand. Because remember, at every specific point, there's an exact direction, left. So your fingers stay left. We're not curling. The curling was to get the general pattern of B. Shake it off. You're no longer curling for right-hand rule number 2. Flat hand, and your fingers will point in an exact direction of, is it an X? Is it a dot? That's why you must use these. It has to be precise. Into, out of, left, right. No fancy, no like approximating, flat hand, straight, exact. So where are we at? And then your palm points in the direction of the magnetic field. So what we get is that the magnetic force is perpendicular to B, right? And the magnetic force is perpendicular to I, or velocity, whichever you're using. So everything's perpendicular to everything. That's how magnetism works. We have 3 dimensions, fingers, thumb, and palm. They're all perpendicular. That's how the right-hand rule works. Your right hand, turns out, can do that very well. That's why we use it. So just a quick example. I'm going to reproduce the 2 wires right now. Current going up. I want it to be straight up. Let me draw that a little better. I'll do the wire in blue. And I want to know what it does to this wire here. I1, I2. So B1 will circle around, thumb up, curling right-hand rule number 1. Tells me that it's going to go dots here and X's here. And it'll be X's here and X's here and X's here and X's here and X's here. B1 goes to infinity. No matter what's over here, it's X's. It doesn't matter what's here. It could be a wall, it could be a universe, it could be a galaxy, it could be empty space, it could be atoms, it could be small, it could be big. It doesn't matter. It circles everywhere. So it circles around. In front of it, it points to the right. I'm drawing in 3 dimensions. In front of it, out of the page, it's going to point to the right. Right here, nothing's there. So where's wire 2? Where wire 2 is, are there dots, X's, left, right? Well, it's X's, because B1 circles around. So just wire 1 is the only thing in the universe. Right-hand rule number 1 creates B1. Pause the video and rewind it to make sure you get that it's X's here. Shake it off. Reset. Right-hand rule number 2, do I know B1? B1 is X's. Write this down like this. I'm not kidding, guys. I2 is up. Right? It's into. B1 is into, I2 is up. So what is FB? Well, my fingers point into. My thumb points up with a flat hand. And if you do that, my fingers, you'll get it. Fingers are pointing into, thumb up. Where does my palm point? Left. Draw that in orange. This adds, right? So palm left. And that is FB. So indeed, I get a leftward force attracting this. So because of the perpendicularity, the symmetry around the rotation is a cylinder. So it preserves that information is transmuted through space. If I turn the wire, the field has to turn with it. So it doesn't produce the same result. So only this model will reproduce this observed outcome. If that didn't make sense, don't worry about it. Or you can rewind it until it does. The point is you can, through this, realize that the only way to do this, the only way to produce attraction, where if I rotate this wire, I should get the same result. And if I make this wire go like sideways, I should not get the same result. The only way to do that is through these 2 right-hand rules. So I did it. And how do I calculate it? Well, I would get the B1 is mu I1 over R, whatever this distance R is, plug that in. And then FB on I2 will be I2 times the length that it is, times its length, times B1. Whatever B1 was, I then plug it into here. That's it. And as long as I'm in amps, meters, and Tesla, and here I need to be in amps and meters, I'm good. And I get however many newtons are on here. I think that's good enough for now. See you guys in class.